Alright, this video is going to be over exponential functions. And please note, if you have some number raised to the power of a fraction, like say m over n, that's equal to the nth root of a raised to the power of m, but it could also be equal to the nth root of a, then raise all that to a power of m. You can write it both ways. Alright, and here's some notes to take about exponents. When you have any real number, with the exception of 1 being raised to a power of some other number, say x, then the following are all true. That number you get when you raise the first number a to a power of some other real number x, that's also in the set of real numbers. And two numbers a raised to one power b and the same number raised to a different power c, those are only equal if the exponents are equal. Now, if your base is greater than 1, say 1.5 or 2 or 3 or 10,000 or whatever, and one exponent is lower than the other, then a to a power of m is less than a to a power of n. So, what that means is, if you let me erase it, if you have picked some number, say 10, if you raise one 10 to the second power and another number to the third, since our base is greater than 1, the term with the larger exponent would be larger. But see part D, where it says if a is between 0 and 1, say 1 over 10 raised to the second, and 1 over 10 to the third. In that case, the number with the smaller exponent would actually be greater, because 1 over 10 squared would be 1 over 100. 1 over 10 to the third would be 1 over 1,000. Alright, here's another example. If f of x is equal to 2 raised to a power of x, find each of the following. First one is f of negative 1. So for part A, f of negative 1 is just 2 to the negative first instead of 2 to a power of x. When you have a negative exponent, remember you can move it to the bottom of a fraction, make it positive. That's 1 over 2 to the first, which is just 1 over 2. Now let me clear some room so we can do part B. Part B, f of 3. That means instead of 2 to a power of x, you'd have 2 to a power of 3, which is, I believe, 8. Part C, f of 5 halves. That means you'd have, instead of 2 to a power of x, 2 to a power of 5 halves. Remember, you can rewrite that as just the square root. Since the bottom number is 2, it would just be a normal square root of 2 to the 5th. That's the square root of 32. Now, I'm going to give the exact answer by factoring down the 32. It'd be 16 times 2. And you know, 16 has a square root of 4, so that would just be 4 times. You can get rid of the 16 until you're left with 2 underneath. That would be 4 square roots of 2. Now for part D, f of 4.92. You start by just plugging it in. And with this decimal number, It'd probably be easy just to get a calculator and plug it in. Because you could convert this 4.92 to an improper fraction and then try to do it that way, but it'd get really messy really quick. So I'd recommend just plugging it into the calculator, and I believe the answer is somewhere in the neighborhood of 30.2. Alright, that previous example was an instance where we would use exponential functions. But pretty much as long as your base is greater than 0 and it's not 1, then you'd have an exponential function. You can have an exponential function, say a raised to a power of x with a base of a. Alright, this first picture, this first depiction of the graph is whenever your base is greater than 1. In this sense, it gives you the example of 2 to a power of x, but it worked for any number greater than 1. Your graph will go in this general direction. Anytime you raise it to a power of 0, it's equal to 1. Anytime you raise it to a power of negative 1, you just put the number underneath 1 as a fraction. And for any positive numbers, you just raise it to that exponent. And the domain is always from negative infinity to positive infinity for an exponential function. And the range, since it's just 2 to a power of x, would be from 0 to infinity. We'll discuss a little bit later what the graph will look like if it's not from 0 to infinity. And since the range is from 0 to infinity, there's a horizontal asymptote at y equals 0, or the x-axis, right here. And when the number is a fraction between 0 and 1, I say here 1/2 raised to the power of x, it goes in the opposite direction above the x-axis. It goes up and to the left, whereas before it went up and to the right. When you raise to a power of 0, it's still 1, but if you notice, the y values are opposite of what they were before. Remember, before you raised the base to a power of negative 1, you got 1/2. Now, since it's 1/2, you'd raise it to a power of positive 1 to get 1/2. Like before, you'd raise it to a power of positive 3 to get 8. Here, you raise it to a power of negative 3 to get 8. So for example 2, it says graph 5 raised to a power of x and give the domain and range. It might be easier if you come up with a table of values. Say when x is negative 1, y would be 5 to the negative first, or 1/5. When x is 0, it'd be 5 to a power of 0, or 1. When x is 1, y is 5. When x is 2, y is 25. So you can plot the points negative 1, 1/5, 0, 1, 1, 5, and 2, 25. If you plot those points, they should allow you to draw the graph fairly accurately, and your graph should look something like this. You notice here when x is 0, y is 1. When x is 1, y is 5. And x is 2, y is 25. So it shows at least 3 of the points we came up with. And those points, as you see, they do allow us to graph it fairly easily. So for the next example, it says graph each function. Show the graph of y equals 2 to a power of x for comparison. And give the domain and range. So Let's start with part A. Start with doing a t-table of x and y values. When x is -1, that'd be -2 to the -1st, or -1/2. When x is 0, it'd be -2 to a power of 0, which is -1. When x is 1, it'd be -2 to the 1st, or -2. Let me write that, see if I can write that a little bit neater. Not really, but you should get the idea of what's supposed to be there. So if you notice, the y values look the exact same as just 2 to a power of x, they're just all negative, which tells you the graph will probably be below the x-axis. In fact, the graph looks something like this. If you notice, you have the black graph, which is just 2 to a power of x on top, then the one we're trying to graph, which is -2 to a power of x on the bottom. Notice you have the points 0, 1, 1, 2, and then 2, 4 on top on the black graph. And then on the blue graph on the bottom, you have 0, -1, 1, -2, and then 2, -4. So what that negative sign in front does is it just flips the graph across the x-axis. Now for the domain and range. The domain for the blue graph, notice it's still going on to the left and right, so the domain would still be all real numbers, or from -infinity to +infinity. And our range, since it's now all the negative y values, the highest y value is 0, so it'd be from -infinity to 0. Part B, it said 2 to a power of x plus 3. Now, what I probably should have done in the first table is, or in the first example part A, is I'm going to do the t-table for 2 to a power of x, so you can have it as a comparison. And I'm also going to do 2 to a power of x plus 3. So when x is -1, y is 1/2. When x is 0, y is 1. When x is 1, y is 2. However, when it's 2 to a power of x plus 3, if you plug in -4 into x, you have 2 to a power of -4 plus 3, which is -1, which is just 1/2. When you plug in -3 in for x, you have 2 to a power of -3 plus 3, which is 2 to a power of 0, which is 1. When you plug in -2, you have 2 to a power of -2 plus 3, which is 2 to the 1st, which is just 2. So if you look, you have the same y values, it's just that the corresponding x values are all shifted to the left 3 units. So what this tells us is that this graph is going to be shifted to the left, the entire graph is going to be shifted to the left 3 units. In fact, if you look at the graph, you have 2 to a power of x, which is their black graph, and then the equation we're trying to graph, which is 2 to a power of x plus 3 in blue. In fact, here it points out one of the points on each graph in comparison, the point 0, 1 on 2 to a power of x. You have the same y value, but the corresponding x value is 3 units to the left. So the plus 3 just shifts it to the left 3 units. Alright, in the domain, since it's going to the left or right, it'd still be from -infinity to infinity. And our range, since it's not shifted up or down any, they're still horizontal. I have put it 0, so the range would be from 0 to infinity. So for part C, f of x equals 2 raised to the power of x minus 2, and then minus 1. Let's first do our table for 2 to a power of x. Next is negative 1, y is 1/2. When x is 0, y is 1. When x is 1, y is 2. Now, let's do it to the power of, let's do it to 2 raised to the power of x minus 2 and then minus 1. Alright, when x is 1, y would be, or the corresponding f of x value or the y value would be 2 to a power of 1 minus 2, which is 2 to the negative first, or 1/2, minus 1, so it would be negative 1/2. When x is 2, y would be 2 raised to a power of 2 minus 2, which would be 2 to a power of 0, which is 1, minus 1 is 0. When x is 3, the y value would be 2 raised to a power of 3 minus 2, which is 2 to the first, or 2, and then minus 1 would be 1. So if you notice, the y values are all shifted down 1 full unit, but the x values are all shifted to the right 2 units. So, if we graph it, the entire graph will be shifted to the right 2 units and then down 1. Look, and here are the graphs for comparison. The blue graph's the one we're trying to graph. Black one is, of course, 2 to a power of x. So the domain, you notice it keeps going on and on to the left and right. So the domain would be from negative infinity to positive infinity. And the range, since we shifted it down 1 unit, instead of it being from 0 to infinity, it's from negative 1 to infinity. So now we're going to learn how to solve an exponential equation. Like if you're told to solve 1/3 raised to the power of x is equal to 81. And 1/3 can be rewritten as 3 to the negative first raised again to a power of x is equal to 81. Remember, 81 can be rewritten as 3 to the 4th. Now you have negative 1 raised to 3 to the negative first raised again to the x. So multiply the exponents, you have 3 to a power of negative x equals 3 to the 4th. So those are only equal, remember, if the exponents are equal. So negative x is equal to 4. Which means x is equal to negative 4. Now, this example is asking you to solve x to the 4/3 is equal to 81. So to start off, you need to get rid of the exponent next to the x. The way you do that is you raise it to a power of the reciprocal. Since our exponent is originally 4/3, you'd raise it to a power of 3/4. But what you do to one side, you do to the other. The reason we do this is because since we have a power raised to another power now, on the left-hand side, you just multiply the exponents. So that would be x to a power of 4/3 times 3/4 equals 81 to the 3/4. The 3's cancel out, the 4's cancel out, so you're left with just x equals 81 to the 3/4. That's equal to the 4th root of 81 to the 3rd which would be the 4th root of, I believe that's 531,441. And the 4th root of that, since we're taking an even root when solving for x, we'd take the positive or negative root. And the 4th root of 531,441 would be 27. So x could be positive or negative 27. Another way to do it is once you got to this point, you could have written as the 4th root of 81. Then once you did that, raise it to the 3rd power. 4th root of 81 is just positive or negative 3 raised to the 3rd power. So if it's positive 3 raised to the 3rd power, it'd be positive 27. And if it's negative 3 raised to the 3rd power, it'd be negative 27. That's another way you could have done it. The next thing we're going to learn about is compound interest. Alright, with compound interest, your final amount, which is your A, is equal to your starting amount, or your principal times 1 plus our interest rate is a decimal, divided by the number of times per year is compounded. Ratio power of, that should be your T in years, times the exponent, or not the exponent, multiplied by the number of times per year is compounded. So it's P raised to the power of 1 plus R over N raised to the power of T times N. Alright, so here's an example. It says, suppose $1,000 is deposited into an account paying 4% interest compounded quarterly. First thing I want to know is, what's the final amount after 4 years? Okay, your final amount is equal to your initial amount or your principal, which in this case would be 1,000. Because remember, let me write the formula right here. It's equal to the principal amount times 1 plus the interest rate divided by the number of times per year is compounded, raised to the power of N times T, with T being the time in years. So it's 1,000 plus 1 plus our interest rate, which is 4%, or as a decimal would be 0.04, divided by the number of times per year is compounded. Since it's compounded quarterly, it says 4 times per year. Raised to the power of time, which is 4, multiplied by our N, which is also 4. So 4 times 4, which is 16. So this would be equal to 1,000 times 0.04 over 4 is 0.01. So 1 plus 0.01 raised to the power of 16. So that's equal to 1,000 times 1 plus, or 1.01 raised to the power of 16. So if you're good, you can type it into your calculator at this point. You could have done it at the beginning, but I want to do it this way just to kind of show you how to simplify it a little bit. Maybe make it easier for you to type it into the calculator so you don't actually hit the wrong button. Now when typing into the calculator, remember you're just raising this part to the 16th power, just the 1.01. And after you raise it to the 16th power, then you multiply it by 1,000. So that tells you the amount after 4 years would be, I believe it's $1,172.58. Remember, when compound interest and talking about money, always just round it to the nearest cent. Alright, and the second part of my question is, how much interest did he make in that time? Or how much interest was made in that time? So, remember, the interest is equal to find out how much interest was accumulated, you take your final amount, subtract it from your principal amount. So that'd be $1,172.58 minus $1,000. That's equal to, that tells you that over the course of 4 years, this account accumulated $172.58 in interest. Alright, for example 8, it says Becky Anderson must pay a lump sum of $6,000 in 5 years. Yes, what amount deposited today at 3.1% compounded annually will grow to $6,000 in 5 years? So, to figure that out, let's look at our formula. P raised to the power of 1 plus R over N raised to the power of N times T. So, we know our final amount would be 6,000. We want to know how much we need to deposit today. So we need to know what our starting amount should be. So that'd be our P. That's equal to 1 plus our interest rate, which is 3.1%. So as a decimal, it'd be 0.031. All over the number of times per year is compounded. Since it's compounded annually, it's only compounded once per year. And then the exponent would be our N times T. Our N is 1 multiplied by our T, which is 5. So to simplify this, that would be 6,000 is equal to P times the parentheses 0.031 over 1 is just 0.031 plus 1 would be 1.031. The exponent 1 times 5 would just be 5. So now, to solve for P, you have to divide both sides by 1.031 raised to the 5th power. And that tells you your principal amount would just be, it'd be $5,150.60, roughly. So if you have this much to invest, then you'll have $6,000 in 5 years with that interest rate. Now for part B, if only $5,000 is available to deposit right now, what annual interest rate is necessary for the money to increase to $6,000 in 5 years? Alright, let's go ahead and plug everything into our formula. 1 plus, your N is 1, so it'd just be 1 plus the R instead of R over N, because since it's compounded annually, we already said our N was 1. And our exponent would just be the time. So our starting amount is 6,000, and we said we only have 5,000. We need to know 1 plus our interest rate, which is R, which we're looking for, raised to the power of T, which is 5. So now, if we divide both sides by 5,000, $6,000 over 5,000 is just 6/5. The 5,000s would cancel out, so you'd have 1 plus the interest rate raised to the power of 5. Now to get to the R, the interest rate, we need to get rid of this 5 as the exponent. So to do that, we need to raise both sides to a power of 1/5. So that tells us we have 6/5 raised to a power of 1/5 equals 1 plus the interest rate, because the 5 and the 1/5 undo each other. So now to solve for the interest rate, we need to just subtract 1. So that would be 6/5 raised to a power of 1/5, and then minus 1 is equal to your interest rate, which means your interest rate is approximately 0.0371, or approximately 3.71%. Alright, so now we're going to talk about continuous compounding interest. Pretty much if it's compounded continuously over time instead of just at some sort of fixed interval or fixed number of times per year, then as you increase the number of times per year it's compounded, you can use the following formula to determine the amount of interest you have. Be the principal, your starting amount, raised to multiplied by e, the natural logarithm or whatever, raised to a power of the interest rate times the time. Now, for this example, it says suppose $5,000 is deposited into an account paying 3% interest compounded continuously for 5 years. So your final amount, because it asks for the total amount after 5 years, the final amount is equal to your starting amount, which is 5,000, multiplied by e, raised to a power of the interest rate, e raised to the power of the interest rate, which was 3%, multiplied by the time, which I believe was 5 years. So that'd be 5,000 times e raised to the power of 0.15, because 0.03 times 5 is 0.15. Now I would tell you the final amount would be $5,809.17.